All right. Hello, everybody. I'm sorry I'm not with you today. As you can tell from how I sound, whatever the virus crud that's going around right now has caught me. A lot of congestion, a little bit of coughing, and was running a little bit of a fever this evening. So, not going to be with you guys today. But we have the technology. We can use it. I should chuckle at technology. I want to spin this around and show you what I've got here. I'm going to mute the microphone because it makes noise as I rotate here. So what you're seeing here is our old trusty document or trusty action camera. It's kind of like a really cheap GoPro that I had laying around. And that's plugged into my computer. I've got a pad of paper down here. I've got a bright light shining on it. I had a similar setup during the pandemic and it worked pretty well. So we're going to give this a try. I'm going to mute to put the, the laptop back where it goes. I'm going to pause here. Oh, there's Lucy. There's our kitten. All right, we'll be right back. All right. Okay, we'll pick back up here. So I just wanted to see the ridiculousness. I didn't do like a full panorama of the document cam. Anybody that's worked with these, you would chuckle to see the number of fittings I've got hooked up to this tripod to actually make this work. I didn't plan on getting sick, obviously, so I didn't grab a document camera from school to borrow and take home. Lucy, if you're going to make a lot of noise, I'm going to kick you out. I'm borrowing. The cats and I share a room, so just ignore the sound of the kitten playing, if you will. Um, okay, I'm going to share screen to my PowerPoint here, and let's look at the notes. So I'm going to move. Yes, Lucy, we're busy. All right. So last time we continued our discussion about velocity and acceleration. We looked at constant acceleration equations, what's sometimes called the kinematic equations. We derived those and we applied those a little bit. So that's a really good place to pick up from. From here, we look at chapter 3 in your textbook. Chapter 3 in this text focuses on vectors. So we've introduced this idea of vectors before, vectors being you have what we call scalar quantities, which are your scalars would be things that any kind of quantity that does not require a direction. I think we mentioned time, for example. I don't know why it's putting that extra line there. I'm just using my mouse. Time, mass. There's apparently some kind of extra mouse input on this laptop. So it's putting extra lines on it there for us. The laptop's deciding to join the party. Time, mass, for example. These are things, time, just this quantity that continues to move forward. Mass, just this amount of material that's present in a situation or a system or an object. So these are, again, these are quantities that we don't require some direction to try to describe adequately. Now, we mentioned we briefly introduced these, I think, last week, talking about vector quantities versus scalar quantities. And a vector quantity being something that requires a direction in order to describe it, right? So a vector quantity, things like we talked about force, for example. I mentioned that, there's a certain amount of force acting on me right now, my weight, pulling me straight down to the center of the earth. So my body behaves one particular way. It doesn't fly off the earth because of that force being directed that way. But there is the option that if somebody or something was to apply that equal amount of weight in a direction towards the camera, towards you right now, my body would behave very differently. And that's going to be our goal in the exam 2 material, the later chapters. We're going to look at Newton's laws of motion and describe how that motion occurs, how forces cause things like acceleration, which causes a change in velocity. And both of those control then a change in position. So force being an example of a vector quantity. Velocity and acceleration are also vector quantities. If we are to indicate something as a vector, right? It's very important that if I'm communicating information, that I'm communicating to somebody that's reading it, whether I'm writing it in my notes or homework, or in the case of a textbook, for example, we want to indicate this quantity as a vector. Well, a lot of textbooks will just simply use a boldface type to indicate something is a vector quantity. Right? Now there are many texts, including yours, for example, that will use a, pardon me. We'll see if Lucy's done. She's settled into her crinkle tube down here. Again, your textbook, for example, uses a hat, just simply a hat, which looks like an arrow. Well, a hat would be half an arrow, or a lot of times they'll just use a small arrow above a vector quantity. And so oftentimes they'll go ahead and continue to use a boldface font in on top of the hat. Now, if we are to do that ourselves, if we were to write a vector by hand, I don't know about you guys. I can't very well do um, a boldface type, for example. A lot of times I need to actually, so I need something other than boldface type when I'm doing it by hand. So a vector notation, if I'm showing a vector by hand, for example, of course, this is physics 1. Organize my notes a little bit. This is going to be L4. This is going to be page 1 of something. So if I want to indicate something as a vector by hand, I'm just simply going to put a hat above it. So a hat being half of an arrow sign. Now, if you want to go to the trouble of drawing a full arrow sign, that's okay. There's nothing wrong with that. But if I'm just doing it, I can do this a lot quicker. And that's just, it's habit for me to be able to do that pretty quickly. So I'll a lot of times do that. Now, going back to PowerPoint here. So you'll want to come up with some way that you can indicate when you're writing things out that you're dealing with a vector quantity. And that's what I would normally do. And where's my mouse? Okay. Now, we talked about displacement is a type of a vector. We talked about displacement being the net distance or the total quantity position change for a particle to go from point 1 to point 2 or final to initial, from initial to final. Now, we've been looking at displacement in one direction along an x-axis or along a y-axis. So we're just looking at just being able to track it by is it moving in the positive x direction or is it moving in the negative x direction? That's all we really need to indicate in that case. However, for us, though, now moving forward, when we're talking about vectors, we need to be able to describe things in more than one direction. So our focus at this point is going to be describing things moving in two directions, both x and y. And we'll talk a little bit about moving in three directions, moving in the z direction. But for the most part, we're going to focus on x and y, two-directional motion. So if we're going to talk about displacement or velocity or any other vector moving in two directions, we need to know how do we do that. So we need to be able to work with vectors effectively. So let's talk about how we work with vectors. So a few things to be aware of. You're going to sometimes have parallel vectors. So parallel vectors are, this is where two vectors have the same direction. You can have equal vectors, which are actually two vectors in the exact same direction and they have the same magnitude. So if they don't have the same magnitude, they're just parallel if they have the same direction. But if they're equal, that means they have the same direction and magnitude. If they're opposite, that just simply means they have the same direction, but they're pointing in different, in opposite directions. They're parallel, but they're pointing in opposite directions here. All right, so if we show that real quick. Nothing complicated, right? It's just one arm. It's a very simple comparison. Parallel vectors, if this is vector A, for example, and then vector B down here, equal, of course, being where, and I'm just representing magnitude as length, right? I'm representing then direction just simply as how it's pointing in the X and Y direction. But you can, when you're drawing vectors by hand, you can describe their magnitude simply by how long you've drawn those vectors. And then again, opposite, where if I've got vector A and then vector B, they can be equal and opposite, which will come up a lot later, especially when we talk about Newton's third law. So equal and opposite is a possibility, but here I've just drawn two vectors that are opposite. They're opposing each other, so different magnitudes, but in opposite directions. So parallel, but just pointing opposite each other. Okay. It's been a hot minute since I've tried to do this between PowerPoint, document camera, and everything in Zoom. So bear with me if it's a little bit rough and slow. I apologize. If you're watching this at home, you could watch it at 1.5 speed if you're comfortable. You can follow along. Okay. Now, if we are to add vectors, we're to combine vectors together, right? So if I were to add multiple displacements together and everything's in the X direction, then I would just add, if something's moved 3 meters in the positive X direction and then 2 more meters in the positive X direction, well, I would just add those together, right? But if they're moving in two different directions, how do we add those together? Well, there's a couple of methods. If I'm adding these vectors graphically, there are a couple of methods that I can use. One is called the head to tail method, which you can see here. I'm going to change my pointer back to a head to tail method. And then the other is a parallelogram method. All right. So if I draw these out, right, adding vectors, we're to add vectors together. Let's say I've got vector A, and then I've got some other vector B. Now, if I want to do the head to tail method, that just simply means I can take vector A, so I'm going to draw it as close as I can to this guy, essentially. And I do have a grid behind me. I could be actually really careful and try to do a very good job of this. So try to copy A as close as I can to what I've got up here. And then I'm going to try to copy B as close as I can to what I've got up there. And so I'd add the tail of vector B to the head of vector A. And then the resultant is what happens when I combine vectors together. So we often call the sum of vectors the resultant. Right? So the resultant would be vector A plus vector B. Now I could add A to B. I could also, interestingly, I could also add B to A and end up getting the same vector. I'm not going to draw that here. It's not, but I can kind of draw it over here. You'll see it when I do the parallelogram method. So the parallelogram method is where I put the two vectors, I put the tails of the two vectors together. So if I put, again, just trying to draw a copy of, let me move up a little bit, that's off the screen. If I draw a copy of A here, and I draw a copy of A, and I draw a copy of B at the tail of A. What I can do then is I can dot in a line parallel to A and from the head of B, and I can dot in a line parallel to B from the head of A. And so now I've got a parallelogram. I've got two equal sides that are parallel here and here for B. I've got two equal sides for A that are parallel to each other. And the resultant would be the vector going from where the two vectors tails meet out to where these two dotted lines meet out there. And again, this would be my resultant in both cases. So I'm essentially getting the same vector. If I pulled a ruler and a protractor out and I drew these exactly A and B exactly the same length all three times and put the protractor to it and got it exactly in the same direction. So I got the magnitude and direction of A and B the same here and here, here and here, then actually the resultant would be the same in both places. Okay. Now, so from there, so that's graphically adding two vectors together. And it's adding, now we're often going to do this mathematically. It's not very often we're going to add vectors together graphically. And we're going to talk about that as we go along here. Well, let's talk about some other things we can do to vectors before we talk about adding them mathematically. So one thing we can do to vectors is we can apply a scalar to them, which basically scales them up or down. So if I multiply a vector by some scalar, let's say lowercase a, and that scalar is larger than 1, the magnitude of vector a will increase, or the magnitude of whatever vector I multiply to will increase. That's if the scalar little a is greater than 1. If the scalar is less than 1, that's going to decrease the magnitude of that vector. And then the negative sign on that scalar is just going to flip the direction of that. So let's look at that graphically real quick here. All right, so for this is page 2 of something. All right, so if I've got vector A again, just a fairly standard vector A, and we want to do scalar multiplication. So if A is greater than 1, then vector A, little a, scalar A times vector A is going to result in something like this. So if this is my vector A, I'm not going to change the direction. All I'm going to do is change the magnitude. So now this is scalar A times vector A. Okay. And we said earlier, if you've got a smaller scalar, right, so something that's less than 1, but we should say between 0 and 1. So some decimal point, right? 0.1, 0.2, 0.5, a half, if you will. Then you would take this direction of this vector up here, but you would make the magnitude much smaller. So you would scale it down, essentially. Right? And then again, if you've got, if A is less than 0, if A is negative, then it's going to be roughly in the same direction, but it's going to be opposite. You've changed it. You've applied a negative sign to it. Okay, so with that in mind, then, what happens if I want to subtract vectors? So we talked about adding vectors together. What happens if I want to subtract vectors? Well, I'm going to multiply one of these vectors by a -1 scalar. That's going to flip its direction. And then I can repeat normal processes for adding a vector that we've already talked about. Yeah, so if I do that then, so let's go back to zoom here. So if I subtract vectors, so if I take, let's say I want vector A minus vector B. Okay, so again, we'll draw a vector A, something like this. Let's say vector B is something like this. Two cats are fighting, so you guys can probably hear that. Apparently, I picked a very active time to try to record a video. So what we're going to do is we're going to take vector A. I'm going to do the head to tail method. So I'm going to draw vector A as it was, vector A. And then I'm going to take vector B here, but I'm going to draw it in the negative direction. So from the head of vector A, I'm going to draw vector B, but in the opposite direction. So vector, in this case, this will be my R vector here from the tail of the first vector to the head of negative B. That would be the resultant would be vector A minus vector B. It would look something like this. Note, very important thing to note here, A plus B, vector A plus B will equal vector B plus A. It doesn't matter if I'm adding them. It doesn't matter which order I add them in. We saw that with the parallelogram method. And let's get that quickly here, right? This is, I don't know if we mentioned that, with the parallelogram method, this is B plus A to get to the resultant, as well as A plus B to get to the same result. So if I am adding vectors, I will get the same quantity. However, if I take A minus B, that is not going to equal B minus A. I will get kind of the opposite. So if I get a positive R here, basically I would get a negative R there is what essentially would happen. Okay. Next then, in today's lecture, there should be a keyboard shortcut I could switch back and forth here. So we know that we can add two vectors together to get a third vector. What if we use this concept to describe a vector? So what if we describe a vector by the sum of two other vectors that are easy to describe? Specifically, what if we describe vector A here? This is vector A. What if we describe vector A here as the sum of A, the amount of A in the X direction, plus the amount of A in the Y direction? Notice what we've done here. I've drawn vector AX and added to it vector AY, and that gives me vector A as a result, right? And I can do it either through parallelogram method or head to tail method, as you see here. Right? This is actually a tool that we're going to use throughout the rest of the semester whenever we're dealing with vectors. Is a very simple thing to do with vectors is break it up into its X and Y components. Notice that these are triangles. These are right. This is a right triangle here. Okay? Vector A, I've got an angle here. This is a right angle because this component's X and Y. So I've got right triangle. We're going to have to do some right triangle trigonometry in order to do this. But that is roughly, well, that's exactly where we're headed right now. I'm going to pause for a moment. Oh, I'm going to pause recording. So looking at kind of doing a basic trigonometry review here. I want to focus on right triangles. I'm not worried so much about secant or cosecant or tangent or cotangent. We're just going to focus on good old SOHCAHTOA. L4 it's 3 of something. All right, so what do I mean by SOHCAHTOA? That means if I've got some triangle up here, right, I've got a right angle on that triangle. Let's say I've got angle, I don't like that. Let's draw this bigger. I got all this room over here. That's a little bigger. So let's say I've got an angle theta down here. Let's say I've got an angle phi up there. We'll make this angle right here right. We'll call opposite of theta, we'll call side A. Opposite of phi here, we'll call side B. And the hypotenuse opposite of the right angle, we'll call C. So a little trig review for us. Okay. Blow the cobwebs off the trigonometry. There's this idea of the SOHCAHTOA, right? SOHCAHTOA. That's not right. Sine opposite adjacent. There we go. SOHCAHTOA. SOHCAHTOA. What does SOHCAHTOA mean? I had to think about it for a minute. What does SOHCAHTOA mean? Sine is equal to opposite over hypotenuse. That's not how you spell hypotenuse, but you guys get the idea. Right? Cosine adjacent over hypotenuse. Tangent opposite over adjacent. SOHCAHTOA. Sine opposite hypotenuse. Cosine adjacent hypotenuse. Tangent opposite adjacent. What do I mean by that? That means that if I take A over the hypotenuse C, well, A is opposite of theta. So this would be the sine of theta because A is opposite of theta. So the sine of theta would be the opposite side of theta, that's A, divided by the hypotenuse C. This would also be the cosine of phi. How do I know that? Well, again, C is the hypotenuse, it's opposite the right angle. So C is going to go in the bottom. And phi, the side adjacent to phi, is A. So the cosine of phi is A over C. And then if I do B over C, well, that's going to be the cosine of theta, which is the sine of phi. And how do I know that? Well, if you look at theta here, well, B is adjacent. B is the other side along with the hypotenuse that makes angle theta. So B is the adjacent side of theta. So if the cosine is adjacent over hypotenuse, so B over C gives you cosine of theta. Phi is opposite of B, so the sine of phi is going to be the opposite side, B over C. And then finally, tangent of theta is going to be the opposite, A, so A is opposite of theta, over B, the adjacent, being the adjacent side of theta. Okay. Now, if I double F. Who can tell me what that means? I'm hoping you're yelling at your computer screen right now or the projector, wherever you're at. That means if and only if, right? If and only if. If and only if theta is measured counterclockwise from the positive x-axis. If and only if theta is measured counterclockwise from the positive x-axis, then your sine of theta is going to be what we call x. No, let's see. Your sine is going to be, your sine is going to be y over r. Your cosine theta is going to be x over r. And your tan theta is going to be y over x. What do I mean by that? If I have I plot x and y here, and I plot some vector r, and we measure it theta counterclockwise from the x-axis. And this length here we can call x, and this length here we can call y, which is also this length. So y is going to be opposite of theta. R will be your hypotenuse. Right? This is basically the radius, or we call this polar coordinates, where I'm measuring angle theta from counterclockwise from x, and r is just out to some point where x and y are going to meet. So if and only if theta is being measured counterclockwise from the positive x-axis, then these hold true. Now, I will tell you this is common in math and physics. It is rare in the real world. I teach later engineering courses. In a statics course, the first thing I try to break students of is this right here. Do not assume sine means y and cosine means x. That because where is theta? Theta is wherever you can measure an angle. That's assuming you can actually measure an angle. Out in the real world, that's a hard thing to do often. We go ahead and teach it here. It goes along with what you're learning in your calculus classes, but I'm rare in the real world. This is a very common thing we'll do in a physics class, and we'll do it in this class, and I'll hold true to it. But I'm just warning you, especially those of you going on to engineering. This is a habit you will drop very quickly once you get past courses like this, and that's okay. It makes a lot of things easy to do this because we actually have a lot of pretty difficult things we're trying to do in a physics and a math class. And so our focus really isn't, figuring out how do we realistically measure an angle. But anyway, we don't have to go too far into that. So this is a nice little trigger view, okay? These are the main things we need to know. The other thing, of course, I'm going to sneak it in up here under tangent because this is a right triangle. The idea of Pythagorean theorem works just fine. A squared plus b squared is equal to c squared. Right? So what does this mean? This means that if I know, basically kind of like we talked about with constant acceleration equations, there's only so many parameters. And there's only, I've got several equations here. If I know theta, right? Another thing to know is theta plus phi plus 90 degrees inside every triangle is 180 degrees. Right. So you look at the number of equations I've got here. I've got 1, 2, 3, 4, 5, 6, 7 equations. And there's only 1, 2, 3, 4, 5, 6, 7. There's only so many parameters there, right? So I really only need to know 1 or 2 values to solve for all the other unknowns around a right triangle. So it's very powerful information given to me. Okay. All right, I'm going to pause for a second. All right, so that's a nice little trig review we've done there. Now, how does that help us? What does that do for us? Well, for one, it allows us to define vectors. It talks about this is how we're going to define vectors, is based on the trigonometry. Okay, so notice here, there are two ways we're saying, well, there's two ways we can define a vector. One is by its components over here. Right? And we're going to talk about these unit vectors in just a second. But basically what we're saying is that if I look at the amount in the x direction and add to it the amount in the y direction, that gives me the a vector, which we mentioned that earlier. And so that means we can define a vector based on its x and y components. So if I know this angle that a is making with the x-axis, then I can figure out both the x and y components just knowing the angle in either the x, y value or the magnitude itself. I can also define a vector in what we call polar form. Right? Polar form means I define the magnitude, or the r, the radius, how far from the origin out to where that vector goes. That's a here, right? So if I have just a, capital A, I'm saying this is vector A with the hat on it over here. This means this is the magnitude of A. The magnitude of A and the direction. So that's what we call polar form. That's where I'm saying this theta, if I put this angle symbol right here, I'm saying this magnitude A at this angle measured counterclockwise from the x-axis. And that would be my theta. How do I find theta? Well, if I know x in any variety, right? If I know y and x, I can take the inverse tangent. That gives me theta. If I know the length in one of these sides, I can use inverse sine or cosine. And again, I can use Pythagorean theorem to find an unknown side of this triangle. So if I know x squared, or if I know ax, the amount of the x direction, the amount of the y direction, I square those, sum them, take the square root, use Pythagorean theorem. That gives me the magnitude of those vectors. Okay, so that's how we would define a vector. We can define a vector based on its x and y components, or its angle, magnitude, and direction in either form. Now, if we back up here, notice I've introduced, without actually introducing them, the I and J vector. These are what we call unit vectors. I and J are what we call unit vectors. I and J point in the X and Y directions respectively. Now they have a magnitude of 1. We talked about unit conversion factors. We said, well, what happens when I multiply by something with a value of 1? Well, I haven't changed anything. So if I multiply by a vector with a magnitude of 1, I don't actually change the quantity I'm multiplying that vector to. All I'm doing is I'm giving the direction of that unit vector. So the I vector has a magnitude of 1, and it points in the x direction. I guess for you guys, it's this way, right? A magnitude of 1 pointing in the positive x direction. So if I multiply something by the I vector, that means whatever that is, let's say 190 pounds for my weight, for example. If I say, well, it's 190 pounds in the I direction, that means it's 190 pounds in the positive x direction. Or 190 pounds in the J direction, that's 190 pounds straight up. And in this case, as they're drawing it here, in the positive y direction. If we do work in the z direction, if we work in 3 dimensions, we use the k vector as the unit vector in the z direction. Okay. As we mentioned earlier, you can add vectors graphically. You want to get out a ruler and a protractor and draw them in an XY coordinate system and draw them at the right angle and the right length. That is perfectly fine. You can do that. It's a nice practice to do that on 1 or 2 of your homework problems. I'm not going to require it necessarily. I don't think the problems, I didn't look too hard. I don't think the problems required a graphical adding addition. You can. It's a nice exercise. I wouldn't do it on every one. It's a neat little practice. We're really going to focus on adding and subtracting vectors using their components. What does that mean? Well, that means that you can see this diagram here. This is a nice diagram from your book. They're saying if I want to add vector A to vector B, Well, notice what they've done. They said, I can take vector A and I can break it into its X and Y component. And then I can add to it the X component and the Y component of vector B out here. And notice that if I add AX to BX, I get the X component of the resultant vector. I love this diagram. It's a beautiful representation of what we're describing here. I can do the same thing in the Y direction. If I take the Y component of the A vector, stack on top of the Y component of the B vector, then that gives me a total resultant in the Y direction. That's what we're saying here. The resultant is going to be the sum of the resultant in the X in the I direction plus the resultant in the Y in the J direction. How do I get those? Well, I add the X component of A and B. That gives me the resultant, the length of how far the resultant goes in the X direction. Add the Y component, A and B. That gives me the length of the resultant in the Y direction. All right, I'm going to pause real quick and grab my examples here. All right. So you can see here, starting example, I've got two vectors here. I've got A, the A vector is in negative 2 times the I direction. That's the X direction, meters. So vector A points negative 2 meters in the X direction. Vector B has X and Y components. Vector B points positive 3 in the X direction. That's the I vector, plus 3I. And then up 2 in the J directions, plus 2J. And both of them are meters. So you could write plus, you could just write 3I meters plus 2J meters. I just like to write the meters one time, so I factored it out. But either way, it works just fine. Now, what we would like to do here is we would like to find vector A plus vector B. We'd like to add these two vectors together. Now, again, you can do this graphically. I can just take this and stack it on this and draw a result between them. We talked about doing that earlier, but that's not normally how we're going to approach these. Normally, we're going to approach these and we're going to say, well, we're going to call this the resultant vector, and the resultant is going to be the sum of Rx in the I direction plus Ry in the J direction. And we said a second ago that Rx, then the magnitude of Rx is going to be the magnitude of A in the X direction plus the magnitude of B in the X direction. And then Ry is going to be the magnitude of A in the direction, the Y direction, plus the magnitude of B in the Y direction. And so all I'm going to do here is I'm going to add up the X and Y components of both these. So A has minus 2 meters. That's its X component. B has a positive 3 meters. So for a net result, I'm going to have 1 meter. So the displacement basically is going to be 1 meter in the X direction. And let's do that for the Y direction. Okay. So if I look at this, the resultant in the Y direction is going to be the Y component for the A vector. And we might look at that and say, well, there's no Y component. We don't know what to do when there's no Y component. No, there is a Y component. It's just 0J, right? There's no Y component. So it's just going to be 0 meters. You could write a J there. I'm not going to. You don't have to write the unit vector when you're just describing the magnitude. So these are just magnitudes. Notice there's no hats on these. So these are just the magnitudes in the X and Y directions. The other one then, so the Y component of the V vector. So it's going to be a positive 2 meters. So 0 plus 2 is just going to be a positive 2 meters. Okay, so what do we do with that? Does that mean we're done? Well, no, we need to define the vector. We could say, and we discussed previously, I could go back and share, but that'd take several clicks. We said there were 2 ways to define a vector. There are 2 ways to define a vector. And here's where I would ask the class, what were they? And I'd wait on somebody to look back in their notes. And one is what we call magnitude and direction, which In your text, they like to call this the polar form. Right? Or we can define it by components. Now, if the problem hasn't specified, most of the time my preference is components because it's kind of easy. If I define it by components, well, the components would be I'm going to take the x component of the result, and that's 1 in the positive I direction, and I'm going to add to it the the y component. Well, that's 2 in the positive j direction, so it's going to be plus 2j, and both of those are meters. So this would be fine. If the problem is not specified, this is using components. And this for me would be just fine. Now, you're going to encounter problems that are going to specify. Go ahead and define it in magnitude and direction, which is going to require you to do a little bit of trig, because most of the time you're going to have the components immediately, because that's the easiest way to combine these. So to get the magnitude and direction, we're going to have to do some trigonometry. Okay. So how do we get there? Well, what do I got here? I've got this resultant kind of looks like this. It's basically I've got 1 meter and 2 meters, and this is my resultant. This is kind of what this looks like. So what I need to know is I need to know what is the magnitude and what is this angle in order to describe r is going to be this r at some angle theta. We call the polar form. Okay. Well, the magnitude of r is going to be the square root of rx squared plus ry squared. So that's going to be square root of 1 meter squared plus 2 meters squared. And that's going to be the square root of 3 meters is what you've got there. And let's see, do I have that written down? I'm sorry, not the square root of 3. It's going to be the square root of 5 meters. I apologize. Square root of 5 meters. And I don't have that number readily available. You'll have to calculate that out. I'll pull a calculator out. I'll just go ahead and pull mine out. And we can look at that. All right. Okay. And we'll go ahead and set up theta here. Theta, to find theta, we're going to take the inverse tangent of, it's going to be x over y. I'm sorry, y over x, right? The inverse tangent of 2 over 1. They're both meters, so you don't have to, the meters over meters is going to cancel out. So, if we do 2, I'm going to do inverse tangent. Looks like my calculator's in degrees, so that's okay. So inverse tangent of 2, that's going to give me about 63.4 degrees would be fine. And then if I take 5, I square root that. So this is, you can see the square root of 5 there is going to be 2.24 meters. So the r vector is going to be 2.24 meters at angle 63.4 degrees. Either answer is just fine if the problem doesn't specify. If the problem specifies components or magnitude and direction, you'll want to go that direction. Pun not intended. All right, let me pause while I get the other example ready. All right, one more example here. I don't know if you guys can tell, my voice is really starting to go. I've been teaching for 20 years at this point, so I know how to get every last drop I can out of my voice, and I can really tell it's starting to fade. So, I might pause a time or two here and skip a few steps just because I don't know if I'm going to get through with the voice I got left, but we're going to try it. Got another example. I'd like to work with you guys here real quick, and we'll pick up from here next time. So this one has a story that goes with it. An individual is walks 180 meters to the west, and then they walk 210 meters east of south at a 45-degree angle, and then they walk another 280 meters east of north, and then they walk a fourth distance. And the fourth distance gets them back to their starting place. We want to figure out what is the vector of that fourth distance. Okay. So what does that mean? Well, if we look at that, basically you're going to have vector A plus vector B plus vector C plus a fourth vector D is going to come back to 0. We're going to add 4 vectors up and we're going to get back to the starting place. The total displacement here is going to be 0. Now, vector A is listed as 100 and, which is a 180 meters west is what they're saying. Well, if you assume north, south, east, and west. So if we assume west is basically the negative x direction, what we're doing is we're saying this is 180 meters in the x direction, in the I direction. Okay, and then the next vector, B, it's described as 210 meters east of south. Okay. So basically they're saying vector B looks like this, 210 meters, and it's east of south. So that means they're saying this is a 45-degree angle here. And then vector C is described as a 30-degree angle. It's 280 meters at 30 degrees east of north. So something like this. C, 280 meters, 30 degrees east of north. Okay. Well, so Steve, what the heck do we do with this? Well, what we want is you want a resultant to be 0, which means the resultant in the x direction added to the resultant in the y direction need to add up to be 0. So what that means is that the resultant in the x direction needs to be 0. And so if the resultant in the x direction is 0, that means when I take A in the x direction, I add it to B in the x direction, and add it to C in the x direction, and add it to this unknown D in the x direction. These should all add up to be 0. And then the same should be true in the y direction. For the vector to have 0, that means both its x and y components have to be 0. Right? So that means all the components in the x and y direction have to all add up to be 0. Okay. And what are we trying to find? We're trying to find, back up here, we're trying to find vector D. We know A, B, and C, or at least enough information to figure them out. We don't know D, but we know the 4 of them are going to add up to be 0. So that's what we're trying to find. What is dx and dy such that these add up to be 0? Well, how are we going to get there? Well, I got to figure out what are the x and y components of B and C, because I already have the x component of A and it has no y component, so that'll be easy enough. All right, so let's look at vector B. Vector B, we've drawn up here. Vector B is pointed in the positive x direction, and it's pointed to the right. So what's the best way to do this? If I let's draw it out a little bit bigger so we can see it here. And vector B looks like this. I've got 210 meters I've got by and bx, and this is 45 degrees. So what I can do here is I can say, well, the sine of that 45 degrees is equal to bx over 210 meters. And I can say that the cosine of that 45 degrees, right, is equal to by over 210 meters. Right? How do I know that? Well, notice bx is opposite of this 45 degrees. by is adjacent to this 45 degrees. This is what I was telling you earlier. Is notice theta here is not being measured counterclockwise from the positive x-axis. Here it's being measured from y. So that means the sine doesn't necessarily mean it's y. The sine is always opposite over hypotenuse. So in this case, the sine of that 45 degrees describes bx. So what that means then is bx is going to be the sine of 45 degrees times 210 meters. And by is going to be the cosine of that 45 degree angle times the same 210 meters. Right. Again, b is going to be bx I plus byj. So vector b, and by the way, I should mention, notice by is pointed down in the negative y direction. So I'm going to have to consider that when I put it in the vector form. Okay. So, all right, let's do this. Let's find out a number for this. So 45 sine times 210, 148.5. So in the positive x direction, I'm going to have 148.5. And it's going to be the same thing because the cosine and sine of 45 are the same. Okay? Cosine of 45 times 210 also, because the sine of 45 and the cosine of 45 have the same value. Now, notice by is pointed down in the negative y direction. So that's going to be minus 148.5 in the j direction. And both of these are going to be meters. That's going to be my y vector. All right, we'll do the same thing with the c vector. Right, I said to move c, he's moving 280 meters, but this one's going to be 30 degrees east of north. So again, that's an angle not measured from the x-axis. That happens. Right? So c is going to be, again, cx in the I direction plus cy in the j direction. Well, this one's going to be both the positive x and y direction. So it's going to be 280 meters. That's going to be my c. It's going to be cy and cx. And again, this angle here is 30 degrees. So that 30 degrees is going to be, you're welcome to do the 60 degrees over here, right? The 60 degrees is going to be opposite of the y if you like, if you really want your sine to be in the y direction, right? What do we know? The sine of this 30 degrees is going to be opposite of cx. So cx is going to be my opposite divided by the 280 meter length. And then the cosine of that 30 degrees is going to be cy divided by that 280 meters. Okay. So if I take 30 times the sine, or the sine of 30 is half, times that 280 is just going to be 140. So if I solve this cx out, cx is going to be the sine of 30 times 280 is going to be 140 meters. And that's positive. It's going to the right. That's positive x. CY is going up, so it's going to be positive y. So CY is going to be the cosine of 30 times that 280. So I'm going to take 30 cosine. Oh, you can't see that. That's going to be the cosine of 30 times 280, 242.5. Okay. So these will go in here. So again, what are we trying to do? We're trying to find vector D. To find vector D, I need to know dx and dy. What do I know? Well, I know the resultants are going to add up to be 0. I've just found the x and y components for my two unknown vectors. So again, I need, if we start in the x direction, I want a resultant in the x direction to be 0. That's going to be the sum of ax plus bx plus cx plus dx. And dx is going to be my only unknown in this equation. So 0 is going to equal, we know vector A, if we go all the way back up to the top, is minus 180 meters. Bx, we said earlier, is going to be 148.5, so plus 148.5 meters. Cx, add to that, is going to be 140 meters, this guy here. And then plus the unknown dx that I'm going to solve for. Okay. So I'm going to take 180. So I'm going to add 180 to this side. And I'm going to subtract 148.5 and 140. So 180 minus 140.5, and then minus 140. 100.5. dx is 100. It's going to be negative 100.5 meters. Okay. So we're actually going to have to walk back in the westerly direction to get back to 0. And then ry, same song, different, same dance, different song. Ay plus by plus cy plus unknown dy. Well, ay is 0. By, we said, was, it's by is actually, b is pointed down in the negative y direction, so it's going to be a negative 148.5 meters. Add to it cy, so you could add a negative here, you could just subtract it. Either way works fine with me. Cy, we said just a second ago, is 242.5. So add, and that's positive, so add to it 242.5 meters. And add to it this unknown dy. So I'm going to add, I've got a 0 here, nothing to do there. I'm going to add this 148 because it's negative here and subtract that one. So I'm going to have 148.5 subtract from that 242.5. I'm going to get a negative 94. So dy is going to show up as a negative 94 meters. So that d vector is going to equal minus 100.5 meters in the I direction and minus 94 meters in the J direction. And if you like, I would say you could round this to 101 would be fine. Let's put this in magnitude and direction, shall we? Let's put this in magnitude and direction. So this vector is 100.5 meters this way, 94 meters down. So this is actually vector D. Vector D looks like this. Okay. So if we put this in magnitude, so I'm going to take 94 squared, add to it 100.5 squared, and take the square root. because the magnitude of d is going to be the square root of dx squared plus dy squared. And that's what I've just done on my calculator here. And that comes out to be, I'm just going to call that 138 meters. So the magnitude of d is 138 meters. I want to find, if I find this angle here, let's call this phi. So phi is going to be the inverse tangent of that opposite is 94 divided by 100.5. So if I take 94 divided by 100.5 and take the inverse tangent, it's almost 45 degrees. It's going to be 43.1. Right? Now, to put it in polar form, vector d would be the magnitude of d and at angle theta, where theta is actually measured counterclockwise from the positive x-axis. Well, I don't have counterclockwise from the positive x-axis. I have counterclockwise from the negative x-axis. That's phi. Right? So theta, in this case, theta would be 180 degrees plus that 43.1 degrees. Right? So d, vector d would actually be 138 meters at angle, and this would be, what is this, 220, we'll say 223, at 223 degrees measured clockwise, counterclockwise from the positive x-axis. So if we put this in magnitude and direction, this is what it would be. In just components, it depends on what's asked. If the problem asks for magnitude and direction, this would be it. If the problem's okay with components, you could leave it like that. All right, that's probably a full lecture. I'm going to stop there. And again, I'm about to lose my voice, so I got to stop anyway.